Apparently, the larger sample is, the less chance for type 2 error. We have seen that just recently, but there are some limits for the sample size as well, because you don't have unlimited resources, right? So what can we find some optimal sample size for some given task, for some given test? Okay, let's recall what the types, the errors depends on. Okay, you remember that type 1 error depends on, first of all, significance level, right? So it's when you reject the null hypothesis, for how small the p-value should be to reject the null hypothesis. But type 2 error depends on many things. It depends on significance level as well. It depends on sample size. It depends on size of effect. And it actually depends on type of test. Actually, some tests are a little bit better in relative to type 2 error. Some tests are a little bit worse. Okay. Well, first of all, which type is more important? Should we decrease type 1 or should we decrease type 2 errors? Okay. What should we sacrifice in this case? Well, it depends, of course. Type 2 error is most important when missing an effect is bad. Okay. For example, in this case, effect, it means contamination. Okay, because our null hypothesis means no effect, no contamination. And in this particular case, it's dangerous if we miss a contamination in a river or contamination in food, if you analyze food or any other things like that. Okay, so in this case, decreasing type 2 errors is quite important. Type 1 error is important when false detection of effect is bad. For example, if you make a new medicine and then you will be, and then you make a test and find out that actually your medicine works quite well. So it means that you will reject null hypothesis, which in this case will mean that medicine doesn't work, right? But then if it's a failure, so you reject null hypothesis, but in fact medicine doesn't work, well, many people will think that your medicine cures them, but it will not. Okay, so in this case, type 1 error is quite dangerous. Now, actually, it's for type 2 errors, it's possible to do some calculations and predict how big the type 2 error will be. Okay. Well, first of all, let me introduce another statistic, which is called statistical power. Statistical power, it's the opposite to type 2 error. So it means that it's a possibility to see effect if it's present. Okay. It's a possibility or probability to reject null hypothesis if indeed null hypothesis is not correct. The alternative hypothesis is true. Okay. So, for example, average content of Vada River, chloride content, of course, of Vada River is 156 milligrams per liter. We make a test, and the null hypothesis is that, that's a mistake, of course. It should be 146 here, 146 milligrams per liter. Okay. So, how likely we will see that the river is contaminated? So, our null hypothesis is that it's not. The reality is that it's contaminated by at least by 10 milligrams per liter above the limit. How likely we will see that it is contaminated? Okay, so this probability is called a power of test, this one. And it's just 1 minus beta, where beta is the type 2 error, the probability for type 2 error. For most of the cases, 0.8, it means 80% chance, is considerably good. But of course, it depends on the case. We discussed that already. Type 2 errors, decreasing type 2 errors is quite important for some of the cases. Okay. Now let me show you how to calculate the statistical power. And the calculation depends on the test you use. For different tests, you have different calculations. Therefore, I decided not to give you the whole theory. It's a bit mathy, but show how to do it in R and give you a couple of examples how you can use the calculation of statistical power. Okay. If we visualize the statistical power, then it's just a simple thing. So you remember that the red area is alpha, and then the blue area, this one, it's beta in this case, right? So because it should be beta, because the statistical power, the power of test is just 1 minus beta, it will be this white area. So every time we have a sample from this, we will be able to reject null hypothesis, and in this case, because our sample is indeed from another population, from this one, this will be a correct rejection. Okay, so that's the chance that we will see an effect when effect is present. So how to calculate it? Let me show you a couple of examples. The first example is following. If we use sample size 10 or 30 and significance level 0.05, let's fix significance level 0.05 in all our examples, and let's assume that standard deviation of our sample is always 10. Okay. Then look, sample size 10 or sample size 30, and the true average chloride content in the river is 154. Okay. 154 is it's 154 minus 146, that's the maximum acceptable limit, is 8, right? So this is the size of effect. How likely we will see this effect if sample size is 10, and how likely if we will see this effect if sample size is 30. Okay, that's the code in R that calculates it. Well, it has many arguments. Let me discuss each of those. This is the function power.t.test, so it calculates the power of t-test. Okay, and then it has this following parameters. This is the sample size. This is the size of effect. It's a difference between the true, the real population average and your null hypothesis. In our case, it's 8. This is standard deviation of your sample, and this is significance level. These are most important parameters. Later you will see that there will be some more. And then there are two parameters that will be fixed. It's what kind of hypothesis we have. In this case, we use one side t-test, right? So we take only one side, not both sides. And then we also use one sample, not two sample. I will not show you here, but you can use this function also for two sample t-test. For example, can you see difference between two groups if indeed it's present? Okay. So that's for n equal to 10, and this is for n equal to 30. Okay, so if I run these two tests, I made a screenshot of our output. So that's the screenshot for the first output. You can see that one sample t-test power calculation, this is n, this is what we have defined. Delta, we also know that. The standard deviation for the sample, the significance level, we knew that, but that's the power calculated value. So 75.4% chance to see this effect where the true contamination is by 8 milligrams per liter larger if the sample size is 10. Okay, if the sample size is 10. What happens if we use sample size 30? So in this case, you see the sample size 30, and the chance is 99.6%. 99.6%. Look, a little bit larger sample, and the chance is almost not 100% for this particular size of effect. Okay. Now, let me show you another example. In this case, we don't know sample size. We want to find it, but we know the desirable power. So the power should be 80% or 90%. So it means that the chance to see the contamination, to see this effect, should be either 80 or 90%. And we keep the size of effect the same. It's 8. Okay. In this case, look, I don't have n anymore. Instead of n, I provided power. Because before I didn't know the power, I just didn't provide it and it was calculated. Now I know power, but I don't provide n, so it will calculate n using power, using effect, standard deviation, and the significance level. Okay, and then I run it two times, one for power 0.8 and one for power 0.9. Let's see what it tells us. So that's the answer for the first case. So the sample size should be around 12 if we want to see this effect as big as this one by 8. And the power should be 80%. Okay. But if we want to see this effect with a larger power, with 90%, then look, we have to take this sample this big. So it's about 15 in this case glasses of water. Okay. So in this case, we know the power and we calculate the sample size. What will be the sample size to get this particular power? And that's one of the most used variation of this function. Okay. And then finally the third. Now again, we know the sample size. And now we know the power at the same time, okay? But we don't know delta. So it means that if we have sample size 10, how big contamination we can see, okay? How big will be the difference between the true population average and the null hypothesis? We can see it with a certain chance, with 80% chance, okay? Or if we take sample size 30, how big the difference we can see? Well, in this case, again, we provide these arguments. We know power now. And we know sample size, and we still provide the standard deviation, significance level, and so on. But we don't know delta. Okay, so I run it twice. For one for sample size 10, one for sample size 30, and this is the result I got for 10. So if we want to see the effect with 80% chance in the sample size 10, that's the delta we will be able to see. So it means that your river should be at least by 8.5 milligrams per liter. In average above this 146 level. Okay, so if it's contaminated, for example, in this case it's 154.5 or larger, then we will see this effect with 80%. But if you get a sample size 30, so the slightly larger sample size, right? So now you can see the effect of 4.7. So it's almost 4.7. So it's almost 2 times smaller effect than what you can see with sample size 10. Okay, so now you can sort of make a trade-off. If you want to see a smaller effect, you have to take a bigger sample size. or you will sacrifice with the power. Okay, but if you want to get a certain power and you want to see a certain size effect, then you can calculate how big the sample size should be. So that's the last slide in this case, and just remember that it's not only p-value that is important, but there are also many other aspects of testing, including the different types of errors, including the power of test, including the possibility to see the effect if it's present, or vice versa, not to see the effect if there is no effect. Okay, so just keep it in mind next time when you use statistical tests.